So we'll look at section 7A, and this is a supplement. We created this section because your book sort of takes for granted that you know how to calculate a sample space, and you would know then, you're automatically going to know how to calculate a sample space, so you would be able to get your probability right off the bat. And we felt like it might be a good idea to show you how to create a way to calculate how many points there are in your sample space. And a common way to do that is either with the counting principle or with the tree diagram. I'll start with tree diagrams. The first example just shows that, okay, well, suppose someone, has in their wardrobe 2 skirts, and then they've got 3 blouses to choose from, and then 2 pairs of shoes. And they might be interested in, well, how many different outfit combinations then are in that person's wardrobe. And what the idea is then is you can read this tree diagram from left to right, and you would see, okay, I can have skirt 1, blouse 1, shoe 1, skirt 1, blouse 1, shoe 2. A quick way to figure out how many total possibilities there are, count your number of ending branches, and you can see there are 2, 4, 6, 8, 10, 12 ending branches. So there are 12 different possibility outfit combinations here with what she has here in her wardrobe. So let's figure out, okay, well, how can we put this together and make our own tree diagram? So for example 2 here, it says a die is rolled, and then afterwards a coin is tossed. We want a tree diagram and the sample space. So when you roll a die, how many options are there? And there would be 6 options, because you can get, it's a standard die. Thinking like a pair of dice, die is just 1. There are 6 options, 1 through 6. And then whenever you toss a coin, there are 2 options. So obviously then 6 times 2 is 12. So I should end up with a tree with 12 ending branches. What I just have done here is I'm already utilizing the counting principle. It's telling me how many times to branch off. So I'm going to branch off in the beginning 6 times. So 1, 2, 3, 4, 5, 6, and I'm going to put 1, 2, 3, 4, 5, 6 off of that. Then it's saying, okay, after you've done that, you're tossing the coin, and you've got 2 options from that. So off of each one of those, you want to branch off twice. And then at the end of those, you want to put what your options are. Well, obviously when you toss a coin, you can have heads or tails. And if you go around and count the number of ending branches, 2, 4, 6, 8, 10, 12 ending branches, and that's what we expected. There to be 12 points in our sample space. Let's go then and let's write out, what are the specific points in your sample space. You might roll a 1 and then get a head, or you might roll a 1 and get a tail. Or you might do a 2 and a head, 2 tail. Likewise for 3s, 4s, 5, as well as 6. And where we're headed in the future is, what's the probability that you would roll a heads? And you'd go through and you'd count, okay, I've got 1, 2, 3, 4, 5, 6 out of the total 12. So 6 divided by 12, and then I reduce it, okay, that's 1/2. What's the probability that you would roll a 2 and a head? So 2 and a head, that only happened 1 time, so that'd be 1 out of 12. What's the probability that you roll a 2 or a head? Or means you can have one or the other. So a 2 or a head, I can count both of these because they both have 2s. This one has a head as well, I just don't get to count it twice. So I get to count both of these, and then I also get to pick up any others that have just a head. So I've got 1, 2, 3, 4, 5, 6, and then I can pick up this one because it has a 2, so that'd be 7 out of 12. So that's where you're headed in later on in our next section. So I just wanted to sort of give you a little foreshadowing there why we're doing this. In example 3 here, it says a coin is tossed 3 times and the outcome is recorded. Draw a tree diagram for this. So if you're tossing that coin 3 times, so let's think about, here's the first toss, second toss, third toss. Each time you toss it, there's only 2 possibilities, heads or tails. Multiply that, and 2 times 2 is 4, times 2 is 8. So there'll be 8 total possibilities. When I go to do my tree diagram, then I branch off in the beginning 2 times with a heads or a tails. That represents the first coin toss. Then I branch off from there, a heads and a tails. That represents now the second coin toss. And then lastly, I branch off one more time, representing my third coin toss, and put a head and tail at each one of those. Again, you should be able to count and see that you'd have 8 ending branches. Read this graph like you read a book from left to right. Head, head, head. Head, head, tail. And my next one. Head, tail, head. Head, tail, tail. And then you come down and do the same thing with the bottom. Tail, head, head. Tail, head, tail. Tail, tail, head. And tail, tail, tail. And then that should be also, listed out here, you would have then your 8 different possibilities. Okay. We'll flip it on over to the next page. The next 2 examples talk about the idea of with replacement and without replacement. With replacement, just like it sounds, that once you choose whatever item you're choosing, then you get to put it back, and then you have the option of actually choosing that item again. Without replacement, like just how it sounds, is once you choose your item, it's no longer in play. So when you go to choose again, there's no likelihood of you choosing that same item. So in part A, 2 cards are chosen from Jack, Queen, King, so just those 3 cards, with replacement. So what that means then is whenever I choose my first card, I've got all 3 cards at my disposal, Jack, Queen, and King. Since I'm doing with replacement, when I go to choose my second card, I'm still going to have all 3 cards to choose from. So I'm still going to branch off 3 times, and I'll have Jack, Queen, King still at that point. And then your sample space, then you can read it left to right. Jack, 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 Queen, Jack, King, likewise Queen, and then read the King, of course, if you can do this without a tree diagram, by all means, it just is the way to help you organize and make sure that you don't miss any of the points in your sample space. Like I said, this is going to be something that's going to be useful for you in the next section. So that would be my sample space. And again, we'd ask you questions like, what's the probability that both of your cards are a king? Oh, that can only happen 1 time out of the 9 possibilities. What's the probability that you would select a king? That can happen 1, 2, 3, 4, 5 times out of the 9 possibilities. All right. In example 4B, this is the idea, same 3 cards this time, and you're just going to still draw 2 cards, but this time it's without replacement. So once I choose my first card, I still have all 3 to choose from. I still have my Jack, my Queen, and my King, but now when I go to choose my second card, since it's without replacement, my first card has already taken 1 out of the loop, so now when I choose my second card, I only have 2 left. And then folks ask me, well, how do you figure out then what goes at the end of these branches? If you think about it, on this branch of the tree, Jack's already been chosen, so the only 2 cards you have left then would be a Queen and a King. On this branch, Queen's already been chosen, so the only 2 cards left would be Jack and King. And then likewise, King's already been chosen, so I have Jack and Queen left over for my second choice. And then your sample space then, Jack, Queen, Jack, King, Queen, Jack, Queen, King, King, Jack, King, Queen. And this just gives you the order of, how you chose your cards. Jack first, Queen second, and so on. I think 4C is the example just below here. I think that will, you should be able to follow that one from what you see there on the solutions key. So we'll flip over to the last page, and this talks more in detail about this counting principle. And essentially, I was trying to show you that already. If you have multiple experiments that you're doing, like in that first example where we were rolling a die and then tossing a coin. Rolling a die, there were 6 different possibilities, and then tossing a coin, there were 2 different possibilities to figure out the number of points in your sample space, I'm just going to do 6 times 2, like we found earlier, 12 total possibilities. So that's a way to figure out how many different possible outcomes there are for a particular experiment. It's So if we look at example 5, we say, okay, you're signed up for courses for next semester. You've got 3 English classes to choose from, 2 maths, and 3 sciences. We want to know how many different sets of 3 courses are possible. So I want 3 courses, first course, second course, third course. And I want an English, a math, and a science. You just go back and look, okay, English-wise, then I have 3 to choose from. Math-wise, 2, and science, another 3. And then I just multiply that. 3 times 2 is 6, 6 times 3, 18 different choices for the courses. Okay. I'll let you try example 6. Let's and you may find in these particular examples you might want to pause the video and then try it for yourself and then see if you can come back. So I'm going to look at example 7 now. So if you want to try it first, pause the video. Here in example 7 it says a restaurant has 7 entrees, 3 veggies, 4 desserts. You want to choose one of each. How many different choices do you have? So I want to choose one from each. So I'm going to draw my 3 blanks. I want an entree, I want a vegetable, and I want a dessert. And entree choices, there are 7, 3 vegetables, 3 vegetables and 4 desserts. Multiply that out and you would find that there will be 84 different lunch choices at this particular restaurant. Let's look at example 8. And again, if you want to try it first, pause the video. How many different 4-letter words, for example, it doesn't have to be a real word here, any sequence of 4 letters is allowed, can be made from these, 8 letters? If in part A, reusing a letter is allowed, so I'm going to have a 4-letter word, so I'm going to draw myself 4 blanks. I can reuse a letter, so my first letter, I've got all 8 to choose from. If I can reuse a letter, then when I choose my second, my third, and my fourth, I still have all 8 letters to choose from. Multiply that out, 4,096 different 4-letter combinations there. Part B, though, says, I still want a 4-letter word, but I'm not allowed to use a letter twice. So what that means here is that when I choose my first letter, I have all 8 to choose from. But when I go to choose my second letter, if I can't use that again, I'm only going to have 7 left to choose from. Then when I get to third letter, I'm only have 6 letters to choose from. Then when I get to my last letter, I'm only going to have 5 left to choose from. Multiply straight across, 1,680 different possible combinations there. I'm going to look on down at example 9. It says pizza to go has 10 toppings to choose from. Suppose you want a pizza with 3 different toppings. How many possible pizza combinations are there? So I want 3 toppings on my pizza. I want them to be 3 different toppings, so it's a little hidden there, meaning it's different. Then when I choose my first topping, I've got all 10 to choose from. So that means once I've chosen pepperoni, I'm not going to put a double pepperoni on there. When I choose my second topping, it's got to be different from pepperoni. I'm only going to have 9 left to choose from. And so then I've chosen, okay, I've got mushrooms. So now pepperoni and mushrooms are out of play. Okay, when I get my third topping, I only have 8 left to choose from. So and this just represents topping 1, 2, and 3. Multiply straight across, and you have 720 different pizza combinations. I'll let you try example 10 with a solutions manual, and then lastly I'll close up here with example 11. It says at a yard sale a person's getting rid of some books. The collection consisted of 10 biographies, 12 suspense, 16 nonfiction, and it says you go and you choose 2 biographies, 1 suspense, and 1 nonfiction. How many different book combinations have you bought? So you're going to choose a biography, then you're going to choose another biography, you're going to choose a suspense, and then you're going to choose a nonfiction. When you choose that first biography, you're going to have all 10 to choose from. But when you go to choose that second biography, you're only going to have 9 left to choose from, because you can't go home with the same book twice. Um, then when you choose your suspense, you'll have all 12 of those. And when you choose your nonfiction, you'll have all 16 of those. Multiply straight across a large number here. 17,280 different book combinations. Um, for example, if you were going to try to do a tree diagram for this particular situation, you would have 17,280 ending branches, because a tree diagram would say, okay, let's branch off 10 times, and then at the end of those, let's branch off 9 times, and at the end of those, let's branch off 12, and then let's branch off 16 from that. And then if you started reading it left to right in order, you would have this many different combinations. So that's the setting up these setups with our counting principle can help you set up your tree diagrams to ultimately get your entire sample space. All right, that concludes this section.